previous lesson, right? On page 30, we basically had a system of inequalities, which is more than one inequality at the same time. However, we deal with one inequality at a time before we start graphing them all together, right? So we did the work for the first inequality here, just like before. What changed though? What changed? Once we had this isolated, we determined that it was a dashed line and that the true region is below, right? Because it's less than, we know it's below. We shaded, but we decided to shade above the boundary line. That's because we're using reverse shading. It's like a tool we're going to use to make it easier for us to find the ultimate solution region, guys. That's why. Because when you have multiple, you're shading all over the place. And it's really hard to tell where is the solution region. So guys, when we do this, we're essentially shading out the false region. We're kind of getting rid of it in a sense. We're like, we don't want that, okay? Then we have the other inequality here. It was facing the same as the other one, so we knew it's a solid line. The true region is below, and we shaded above as well. So we did reverse shading. I'm going to write that down here. That's why we're doing that, okay? Reverse shading. So when it came down to graphing both of these lines, we shaded out, like basically everything you see shaded is false. Those are false regions, okay? Those are regions we don't really want. We don't care about them. And so what you're left with, like the area that is not shaded, is therefore the ultimate solution region for both inequalities present, okay? We're only going to go as far as 3 inequalities at the same time, okay? So after this, the extra layer would be 3 inequalities. So can you imagine having 3 inequalities and shading, doing regular shading and having to find out which one is the darkest region? That is the solution region. That's going to be very hard for you to do that with without software, okay? So let's go to 29, and I'm just going to show you what I mean by that. So 29. So when you have a system, okay, when you have a system, we're going to use reverse shading. So having multiple solution regions makes it difficult to determine the solution region for all inequalities. To make it easier, here it is. Highlight this part. To make it easier to determine the overall solution region, we used reverse shading with systems. And what does that mean? It essentially means that we shade out the false region in order to figure out the solution region. So here is, I use Desmos for this. So this is regular shading here. What does that mean? True region true regions shaded. So every inequality that you would have isolated and done work with, right? That's what it would look like. That's what that graph would look like. And I kind of gave it away a little bit because I was using this to make a point yesterday. But can you tell which one is the darkest region by looking at that piece of paper right now? Can you tell absolutely definitively though? Would there be times where you would guess a little bit? I think you can see that this little triangle is the darkest region. We've got here, we've got some shading here, here, here. So there's overlaps, but this is the ultimate overlap. This one right here is true for this one, is true for this one, is true for that one. So all three inequalities, this is the true region for all of them. And so this is the ultimate solution region. If we do this by hand, it's going to be very, very hard to determine the ultimate solution region. So that's why we do reverse shading, right? Reverse shading is false regions shaded, okay? False regions are shaded. So let's go over to the first one, and we still will decide that this right here, sometimes it's closed up on every side. This is the solution region. So if we do reverse shading, it's much easier. It's very obvious that this is going to be the one that's the solution region. Okay? So that's the main reason we do that. It's a tool. It's a tool, that's it. Okay? The next thing that we need to account for, so we're going to use reverse shading, so let's circle this as what we're going to use from now on. And the next part is this one. I call them points of intersection or corner points. So POI or corner points. It's where the boundary lines meet surrounding the solution region system. So in this case, we've got 1, 2, 3 corner points. Okay? These are all the POIs or the corner points. Over here, this system has a solution region here, and this is the corner point. So sometimes you just have one POI, sometimes you have several. So basically you want to go along the boundary lines that surround your solution region, and if there are two lines that meet, you want to identify that point. Okay? So let's go to page 30 and finish what we started. Okay? We need to do this part yet on page 30. So how do we do that? We put this into, I'll do this, y1. I'm going to enter 4 over 6 x minus 2. y2, I'm going to enter the second equation here, negative 2 over 3x plus 3. And then we're going to go second, trace, intersect. Second, trace, intersect. So let's go and grab our calculators and practice this, okay? I said this before, I'll say it again. Use brackets for the leading coefficient, right? 4 over 6, x minus 2. And then the second one, I'm using brackets. You got to go negative 2 over 3, x plus 3. And yes, you're going to have to review Zoom. Why is it that? There you go. That's better. Oops, I got to clear that one. My bad. Let me first clear this. I was doing other stuff. Clear. So if you graph, it could be that you don't really see the whole thing. I see glimpses of it. So let's do a standard zoom. Do you remember that? If you want to zoom, zoom standard gets you to a standard 10 by 10 window. And that, in this case, that'll do a pretty good job for me. Okay? And you should see, it's not going to look identical to what you have on here, but you should see similarities of the resulting shape. Okay? So we want to find that point of intersection right here. I'm going to use a red pen for that one. It's where those boundary lines meet. That is what we call, in this case, this is the only POI, the only point of intersection we have available to us. So we're going to go second, trace, intersect. If you only have 2 lines, you don't really need to worry about getting closer to it. You just hit enter 3 times. If you've got more than 2 lines, that gets a little trickier. I'll show you that. Enter, enter, enter. And there it is. It'll usually be worth a full mark if you have to use your calculator for this. There you go. 3.75, 0.5. So let's write that down. So somewhere on this paper, whether you want to do it on the graph itself, I prefer, if I ask you for the POIs, to do that separately on the side. Okay, so that would probably usually be it, but I also need to show you how to do this part right here. Is 4, 5 a solution to the system? Because we have the graph, we can actually determine that fairly easily. If we go over here, where is 4, 5? 4, 5 is over here. It's not in our solution region. We know it's not going to be a solution. But I'm going to ask you this without a graph. So how would you show it without a graph? You substitute sub into, watch this, all inequalities. If you have 5 inequalities, you need to enter this into all 5 and check if it's true for all of them. Okay? If true for all, then it is a solution. Okay? If it's true for all, then we will consider this a solution. So let's do inequality 1. So I prefer to grab the originals, guys, for this one. This is just in case you made a mistake, right? So if you grab the very originals, this is what we've got, the non-cleaned up version. 4 goes in there, and 5 goes into the y. We have company. Anyways, 16. This is 30 plus 12, that's 42. What do you think? True or false? False, right? It's when it comes to negatives that students have a problem. Therefore, not a solution. And you might say, shouldn't I check the other ones, Mr. Dirksen? It doesn't matter. If it's false for one, it's false for the system. You understand that, guys? If it's false for one of them, we're not going to use it because we want it to be true for every single one of them. Since it failed the very first time, we're done. Okay? If this had been true, you would have had to keep checking until you find a false one. Or else, if it's true for all of them, then we say it is a solution. Okay? So keep that in mind. All right. I'm going to ask you, it could be that you already finished 31 and 32, but I have a feeling that you didn't. I don't know if you knew what POIs were. I'm not sure. Okay. I will do one more with you, a special case. I find them easier actually, but students miss it sometimes. So I'm going to go to 31 if you wouldn't mind.